We were wrong, not partially wrong, not wrong in the peripheral correctable way that science is routinely wrong when a measurement needs refinement or a model needs a new parameter. Wrong at the level of the question itself. Wrong about what we were asking, wrong about what beginning means, wrong about whether the Big Bang, the event that every cosmology textbook describes as the origin of everything, the moment when space and time and matter and energy all burst into existence from an infinitely dense singularity, was actually the beginning of anything at all. And here's what makes this particular wrongness so extraordinary. The evidence that we were wrong didn't come from some new telescope observation that overturned the existing picture. It came from following our own best theories more carefully than we had before. From taking the mathematics of inflation, the theory that describes the very early universe, and asking what happens when you trace it not just forward in time, but backward, and then further backward. And then asking the question that physicists had largely avoided asking: what was there before? The answer that comes back from multiple independent lines of theoretical reasoning, from thermodynamics, from quantum field theory, from the mathematics of eternal inflation, is not nothing. It's not the question doesn't make sense. It's not time itself began at the Big Bang, so there is no before. The answer is something. Something that was there before the Big Bang, something that generated the Big Bang, something that has been generating Big Bangs plural continuously, perhaps eternally, and something that means the universe we inhabit is not the universe. It's one universe among an effectively infinite number, each one born from the same underlying process, each one with potentially different physical constants, different particle physics, different histories. The Big Bang wasn't the beginning. It was a transition, a phase change in the state of the cosmos, a local event in a much larger, much older, perhaps infinitely old structure. That's what I want to explore. Carefully, rigorously, following the physics wherever it leads. Because this is one of those ideas that sounds almost mystical when stated baldly before the Big Bang. There was something, there were other universes, and becomes genuinely scientifically compelling when you trace the reasoning that leads there. Let's trace the reasoning. Start with what we know, or rather, start with what we thought we knew. The Big Bang model is one of the great triumphs of 20th century science. The observational evidence for it is overwhelming and comes from multiple independent directions. The universe's expanding established by Hubble in the 1920s, from the recession of galaxies confirmed by every subsequent measurement, extrapolating backward, the universe was smaller, denser, and hotter in the past. About 380,000 years after the beginning, it was hot and dense enough that electrons and protons couldn't form neutral atoms. The universe was an opaque plasma. When it cooled enough for atoms to form, the universe became transparent, and the light from that moment has been traveling toward us ever since, stretched by cosmic expansion into the microwave region of the spectrum. This is the cosmic microwave background, the CMB, which we've discussed in other conversations and which has now been mapped with extraordinary precision. The CMB matches the predictions of the Big Bang model with spectacular accuracy. The abundance of hydrogen, helium, and lithium in the universe forged in the first 3 minutes by Big Bang nucleosynthesis matches the model's predictions precisely. The large-scale structure of the universe, the cosmic web of galaxy filaments and voids, is consistent with structure growing from tiny initial density fluctuations over billions of years of gravitational amplification. The Big Bang model works remarkably well. It correctly describes the universe from about 1 second after the beginning to today, 13.8 billion years later, over essentially all of the universe's observable history. But here's the thing. The Big Bang model has a problem, several problems actually, problems that were recognized in the late 1970s and early 1980s and that the model by itself cannot solve. Problems that point directly at something that must have happened before or instead of the simple, featureless Big Bang singularity. The first problem is called the horizon problem, and understanding it requires understanding something about how light and information travel in an expanding universe. The CMB is extraordinarily uniform. The temperature of the CMB, the relic radiation from the early universe, is the same in every direction you look, to better than 1 part in 100,000. Whether you point your antenna at the north celestial pole or the south, whether you look in the direction of the Virgo cluster or directly away from it, the CMB temperature is 725 Kelvin everywhere, to extraordinary precision. Now here's why this is a problem. Consider 2 points on opposite sides of the observable universe separated by about 93 billion light years. These points were never in causal contact. Light from one side has never had time to reach the other side. The universe is only 13.8 billion years old, and the separation is 93 billion light years. Information cannot travel faster than light. So these 2 points have never communicated, they've never exchanged energy or information, they've never had any opportunity to reach thermal equilibrium. And yet they're at the same temperature, to 1 part in 100,000. In ordinary thermodynamics, 2 systems reach the same temperature by exchanging energy by being in contact long enough that heat flows from the hotter to the cooler until equilibrium is reached. A cup of hot coffee in a cold room reaches room temperature because the coffee molecules interact with the air molecules, exchanging energy, slowly equilibrating. But the 2 opposite points in the CMB have never interacted. They were, at the moment the CMB was emitted, already separated by a distance that no signal could have crossed since the Big Bang. So why are they at the same temperature? In the standard Big Bang model, this is just a coincidence. A really, really extraordinary coincidence, because it's not just 2 opposite points. It's every point in the CMB, in every direction, all at the same temperature, all apparently having equilibrated with each other despite never having had causal contact. The probability of this happening by chance, of all these causally disconnected regions of the universe happening to have the same temperature without any physical mechanism to enforce it, is not small. It's essentially 0. The horizon problem is not a minor puzzle. It's a fundamental, deep problem for the standard Big Bang model. The second problem is called the flatness problem. General relativity tells us that the geometry of the universe, whether it's flat, positively curved like a sphere, or negatively curved like a saddle, depends on the density of energy and matter it contains. There's a critical density, a specific value, such that a universe with exactly that density has flat geometry. A universe with more than critical density is positively curved. A universe with less is negatively curved. Our universe is extraordinarily flat. Measurements of the CMB, particularly from the Planck satellite, show that the universe's geometry deviates from perfectly flat by less than about 0.4%. The density of the universe is within 0.4% of the critical density. This sounds like it might just be a coincidence of values. But here's why it's a profound problem. In the standard Big Bang model, flatness is an unstable equilibrium. A universe that starts with exactly critical density will maintain that density forever perfectly balanced. But a universe that starts even slightly above or slightly below critical density will diverge, it will become more and more curved over time. The flatness will not be maintained, it will get worse. To be as flat as we observe today, the universe at the Planck time 10⁻43 seconds after the Big Bang must have had a density that differed from critical density by no more than about 1 part in 10⁻60. 1 part in a million trillion 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 trillion. The universe was flat to 60 decimal places at the Planck time. Not because it had to be, because of some physical mechanism that enforced it, but apparently by coincidence in the standard model. The probability of this initial flatness being a coincidence is so small that it's effectively impossible. Something must have made the universe flat. The standard Big Bang model has no answer. The third problem is the monopole problem. Grand unified theories attempts to unify the strong nuclear force with the electroweak force predict that in the hot, dense conditions of the early universe, exotic particles called magnetic monopoles should have been produced in enormous quantities. A magnetic monopole is a particle with a single magnetic pole, like a north pole without a south. Maxwell's equations allow them in principle, and grand unified theories predict they should exist. In the early universe, they should have been produced abundantly, but we don't observe magnetic monopoles. Not one has ever been detected, despite extensive searches. Either grand unified theories are wrong, which is possible, or something happened in the early universe that diluted the monopole density to unobservably low levels. The standard Big Bang model doesn't explain the absence of monopoles. 3 deep problems, 3 things the standard Big Bang model cannot explain. And in 1980, a young physicist named Alan Guth proposed a single, elegant mechanism that solved all 3 simultaneously. Guth's proposal was inflation, a period of extraordinarily rapid exponential expansion of the universe in its very earliest moments, beginning perhaps 10 negative 36 seconds after the Big Bang and ending at around 10 negative 32 seconds. During this unimaginably brief interval, the universe expanded by a factor of at least 10, 26, 100 million, trillion times. Some versions of inflation predict expansion by factors vastly larger than this. How does inflation solve the 3 problems? The horizon problem. Before inflation, the region that would become our entire observable universe was extraordinarily tiny, small enough that all of it was in causal contact. All of it could exchange energy and information and equilibrate. Inflation then stretched this tiny, already equilibrated region into the vast expanse we observe today. The uniformity of the CMB is not a coincidence. It reflects the uniformity of the pre-inflation region, which had time to equilibrate because it was so small. The flatness problem. Inflation stretches any initial curvature to near perfect flatness in the same way that the surface of a basketball looks curved, but the surface of the Earth appears flat because the Earth is so much larger. Any initial curvature of the universe is stretched to imperceptibility by inflation's factor of 1026 expansion. The flatness we observe is a prediction of inflation, not a coincidence. The monopole problem. Inflation dilutes any previously produced monopoles or any other exotic particles to negligibly low densities. If monopoles were produced before or during inflation, they were spread across a volume so vastly larger than the observable universe that the probability of one being in our observable region is essentially 0. 3 problems, 1 solution. Inflation is beautiful in the way that the best physical theories are beautiful. It solves multiple unrelated puzzles with a single, simple mechanism. But inflation also does something else, something that Guth and his collaborators recognized almost immediately, and that has become one of the most important and most contested ideas in modern cosmology. Inflation doesn't just happen once. It keeps happening everywhere forever. Here's why inflation is generically eternal and why this matters more than almost anything else in modern cosmology. Inflation is driven by a field, the inflaton field, that permeates space and has energy stored in it, similar to the way a compressed spring has potential energy stored in it. When the inflaton field has a large value, it drives rapid exponential expansion. Eventually, when the field rolls down to a lower energy state, like a ball rolling down a hill, inflation ends. The energy stored in the inflaton field converts into heat and matter. The universe becomes a hot, dense plasma. The standard Big Bang physics begins. But here's the subtlety that makes inflation eternal. The inflaton field is a quantum field, and quantum fields are subject to quantum fluctuations, unavoidable, irreducible, fundamental, random fluctuations that arise from the Heisenberg uncertainty principle. In any region of space where inflation is occurring, quantum fluctuations are continuously jostling the inflaton field up and down. These fluctuations compete with the classical tendency of the field to roll downhill toward lower energy. In most places, the classical rolling wins, the field rolls down, inflation ends, a hot Big Bang occurs. But in some places, by quantum chance, the fluctuation pushes the field back up the hill, maintaining or increasing its value, keeping inflation going. In these places, inflation continues. And here's the crucial point. Inflation is exponential expansion. A region where inflation continues doubles in size every tiny fraction of a second. The regions where inflation ended, where the field rolled down, are expanding at normal cosmological rates. But the regions where inflation is still occurring are expanding exponentially faster. They're doubling in size constantly. They're growing far faster than they're converting to post-inflationary regions. The result is that the total volume of space where inflation is still occurring never decreases. Despite the constant local conversion of inflating regions into post-inflationary regions, each one producing a hot Big Bang, the inflating volume is always growing faster than it's shrinking. There is always more space being created by inflation than is being converted to non-inflating regions. This is eternal inflation. Once inflation starts, it never stops globally. It ends locally in each region that quantum fluctuations allow to roll down, but globally, inflation persists forever. The universe as a whole is always inflating. Our entire observable universe, the 93 billion light-year sphere we can see, is one of these local ending points, one pocket in an eternally inflating sea. One bubble of post-inflationary Big Bang physics surrounded by still inflating space that we can never observe, that is continuously generating more bubbles. Let me try to make this more concrete with a thought experiment, because the abstract description can obscure just how radical this picture is. Imagine an eternally inflating universe as an ocean, a vast, expanding ocean that has been growing since before our universe began and will continue growing forever. Within this ocean, bubbles occasionally form regions where the inflaton field happened to roll down, ending inflation and beginning a hot Big Bang. Each bubble is a universe, a pocket universe, an island in the inflating sea. Our observable universe is one of these bubbles. It began 13.8 billion years ago when inflation ended locally, when the inflaton field in our region rolled down and converted its energy into heat and particles. That moment was our Big Bang. But the Big Bang was not the beginning of everything. It was the moment our bubble formed in the pre-existing inflating ocean. Before our Big Bang, in the inflating sea space, was already there. Time was already there. Physics was already operating. The inflaton field was already doing its thing, driving exponential expansion, generating quantum fluctuations, producing bubbles. Our Big Bang was not creation ex nihilo. It was a local phase transition in a pre-existing physical process. This is what I mean when I say the Big Bang wasn't the real beginning. It wasn't the beginning of space. It wasn't the beginning of time. It wasn't the beginning of the laws of physics. It was the beginning of our local region, our bubble, our particular patch of the cosmos. Momentous for us. Cosmically, just one more bubble in an eternal foam. Now, I want to address something that I think is crucial to engage with honestly, because the eternal inflation picture is extraordinarily compelling theoretically, but it has a problem that its proponents acknowledge and that its critics emphasize. The problem is observational inaccessibility. The inflating sea, the region outside our bubble, is, by construction, beyond our observable horizon. We cannot see it. We cannot detect it directly. The other bubbles, the other pocket universes, are separated from us by eternally expanding, inflating space that no signal can cross. We are causally isolated from them. This raises a serious question about the scientific status of eternal inflation. If the central prediction of the theory, the existence of an inflating background and other bubble universes, is unobservable in principle, is it science or is it metaphysics? Is it a legitimate physical theory or an untestable speculation dressed up in mathematical language? I want to give this question the honest answer it deserves. It's a real concern, and it's one that the cosmological community takes seriously. But here's the response. First, just because something is not directly observable doesn't mean it's outside the scope of science. We cannot directly observe the interior of a black hole, the moment of the Big Bang, or the quantum state of a single electron before measurement. We infer these things from their consequences, from observable predictions they make about things we can measure. Eternal inflation makes predictions that are in principle observable. The distribution of properties, the density fluctuations, the spatial geometry, the physical constants in our bubble reflects the statistics of how bubbles form in the eternally inflating background. These predictions, in principle, could confirm or refute the eternal inflation picture. Second, some versions of eternal inflation make predictions that are more directly testable. If our bubble collided with a neighboring bubble at some point in the past, a collision between two pocket universes, the collision would have left a specific calculable imprint on the CMB. A circular anomaly with specific temperature and polarization properties. We haven't found such an imprint in current CMB data, but the search continues, and future CMB measurements might detect it or rule it out at higher confidence. Third, the eternal inflation picture is not an add-on speculation. It's a generic, almost unavoidable consequence of the inflationary physics that we already have strong evidence for. Inflation is supported by the same CMB observations that have become the bedrock of modern cosmology: the flatness of the universe, the uniformity of the CMB, the specific pattern of density fluctuations. If you accept inflation, and the evidence for it is strong, eternal inflation follows almost automatically from the same quantum physics that governs everything else. You don't have to add extra assumptions. You have to add extra assumptions to avoid it. But here's where the story gets even deeper and more uncomfortable. Eternal inflation doesn't just tell us that the Big Bang wasn't the beginning. It tells us something about what might have preceded inflation itself. The eternally inflating universe has been inflating for a very long time, possibly infinitely long. But can it have been inflating for literally infinite time? Is there a sense in which even eternal inflation had a beginning? In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem now called the Borde-Guth-Vilenkin theorem, or BGV theorem, that addresses exactly this question. The theorem shows that any space-time that has been expanding on average must have a past boundary, a beginning. Even an eternally inflating universe which expands on average cannot be past eternal. It must have had a beginning at some finite time in the past. This is a remarkable and somewhat unexpected result. It says that even the inflating sea, the vast eternal background that generated our Big Bang, had its own beginning. There was a time before which even inflation didn't exist, and before that time something else must have been occurring. What was it? Here, the physics becomes genuinely uncertain. The BGV theorem identifies a boundary, a past boundary of the inflating space-time, but it says nothing about what's on the other side of that boundary. The boundary is where classical general relativity breaks down. It's a place where the curvature of space-time becomes infinite, a singularity in mathematical terms. And singularities, as we've discussed in our conversation about black holes, are places where our current theories fail. They're not physical predictions, they're confessions of theoretical incompleteness. Beyond the past boundary of eternal inflation, quantum gravity must take over. And in the quantum gravity regime, where the universe is small enough and hot enough that the quantum nature of space-time cannot be ignored, the concept of before may not apply in the classical sense. Time itself, as a continuous, well-defined variable, may dissolve into quantum uncertainty. This is the deep frontier, the place where our best theoretical tools, quantum field theory, general relativity, inflationary cosmology, all reach their limits simultaneously. The place where, to answer the question, what was there before, we'd need a complete working theory of quantum gravity, which we don't have. But we have ideas. Some of them are genuinely profound. Let me tell you about the two most serious proposals for what preceded the beginning of eternal inflation, for what created the inflating universe in the first place. Because these proposals don't just push the beginning back further, they challenge the very concept of a beginning in ways that I find genuinely mind-expanding. The first is the Hartle-Hawking no-boundary proposal. In 1983, James Hartle and Stephen Hawking proposed that the universe might have originated from quantum tunneling from literally nothing, not from a prior state, not from a pre-existing physical system, but from the quantum vacuum itself. Not the quantum vacuum in the sense of empty space, which we've established is not nothing, but seething with quantum fluctuations. But from a mathematical state of zero volume, zero time, zero everything, in the Hartle-Hawking picture, the universe has no boundary in time. Time itself emerges from a more fundamental description in which there is no time only, space, described by a quantum wave function. At the beginning, time transitions from a spatial dimension, imaginary time, in the mathematical language, to a real temporal dimension. The Big Bang in this picture is not a singularity at the edge of time. It's a smooth, rounded beginning, like the South Pole of a sphere. There's no before the South Pole. Not because time had a wall there and you can't go further, but because the concept of southward loses meaning at the South Pole itself. The Hartle-Hawking proposal is mathematically elegant and philosophically radical. It suggests that the universe didn't need a cause, not because causality doesn't apply, but because the beginning wasn't a boundary in time requiring a prior cause. It was a smooth transition from a timeless quantum state to a state with time. The second proposal is Alex Vilenkin's tunneling from nothing. Also developed in the early 1980s, Vilenkin's proposal is similar in spirit but different in mathematical structure. The universe tunneled quantum mechanically from a state of zero size, nothing, to a small but non-zero size, from which inflation then drove the subsequent expansion. The tunneling probability is finite and calculable. The universe didn't need infinite time to form. It popped into existence from a quantum fluctuation in literally nothing. Both proposals grapple with the same profound question: why is there something rather than nothing? And both answer it tentatively, speculatively, but with genuine mathematical content by saying that nothing is quantum mechanically unstable, that the laws of quantum mechanics applied to the state of absolute nothingness inevitably generate something, that the universe is what happens when you apply quantum mechanics to the void. I want to pause here and do something that I think is important. I want to be completely honest about the epistemic status of everything I've just told you. Inflation, the basic mechanism, is strongly supported by observation. The CMB evidence for it is compelling. The flatness of the universe, the uniformity of the background, radiation, the specific spectrum of density fluctuations, all of these are consistent with inflation and are difficult to explain without it. Inflation is not proven. Science doesn't prove things, but it's well supported. Eternal inflation, the extension of inflation to a global, never-ending process, follows mathematically from the same physics almost unavoidably. If inflation happened at all, it almost certainly happened eternally. The BGV theorem is mathematically rigorous and broadly accepted. The implications of eternal inflation, the multiverse of bubble universes, are genuine consequences of well-established physics, not speculative additions. But the Hartle-Hawking and Vilenkin proposals, the ideas about the universe tunneling from nothing, are much more speculative. They're genuine proposals by serious physicists with real mathematics behind them, but they're not tested. They're not uniquely determined by the physics we know. They're educated guesses about the regime where our physics breaks down the quantum gravity regime before the beginning of inflation. The honest answer to what was there before the Big Bang is we don't know. We have ideas. Some of them are beautiful and mathematically serious, but none of them is established. What is established, what I am confident in saying, is that the Big Bang was not the beginning. The eternal inflation picture is well grounded enough that the universe almost certainly extends before our Big Bang in a pre-existing inflating background. The Big Bang was a transition, not a creation. What that background itself emerged from, whether it had a beginning, whether before applies to it, is genuinely open. And that openness is not a failure. It's an invitation. It's the frontier of the deepest question in cosmology, pointing at the deepest gap in our physics, demanding a theory of quantum gravity that we're still building. Let me end this first part with something that I think puts all of this in the right perspective. The history of cosmology is a history of the horizon receding. Every time we've built better instruments, developed better theories, extended our mathematical reach further backward in time, the beginning has moved. The ancients thought the cosmos was eternal and unchanging. The Big Bang model pushed the beginning back 13.8 billion years to a specific physical event. Inflation pushed it back further to a period before the Big Bang, to an exponentially expanding early universe. Eternal inflation pushes it back further still to a pre-inflationary background with no clear beginning. The Hartle-Hawking and Vilenkin proposals push it to the edge of the concept itself, to a quantum origin that may not have a before in any classical sense. Each step has not just moved the boundary, it has changed our understanding of what the boundary is. Each step has made the universe larger, older, stranger, more extraordinary. And each step has left us with deeper, harder questions than we started with. We were wrong to think the Big Bang was the beginning, but being wrong was the right thing to do. It was the honest answer given what we knew at the time. And discovering we were wrong has led us here to a picture of the cosmos that is so much richer, so much more extraordinary than the one we replaced. In part 2, I want to dig deeper into what the multiverse of eternal inflation actually implies. Not just as a theoretical construction, but as a physical picture of reality with specific testable consequences. I want to tell you about the measure problem, one of the deepest and most technically demanding puzzles in theoretical cosmology, about what it means for the laws of physics themselves to vary from bubble to bubble, and about why the anthropic principle, which most physicists have spent decades trying to avoid, may turn out to be not a philosophical cop-out, but a genuine physical necessity in an eternally inflating universe. Because if there are infinitely many bubble universes, each with different physical constants, then the question of why our universe has the specific constants it has, why the electron has the mass it has, why the cosmological constant is the tiny but non-zero value it is, gets a completely different kind of answer than the one physics has traditionally sought. Not the answer, because these are the only values consistent with the laws of physics. But the answer, because these are the values consistent with the existence of observers. And that distinction between a universe that must be this way and a universe that is this way because we're here to observe it is one of the most profound and most unsettling shifts in how we think about the laws of nature. We were wrong about the Big Bang being the beginning. We may also be wrong about what it means to explain the laws of physics. And working out what right looks like is where we're going next. So we'd arrived at this extraordinary place where the Big Bang wasn't the beginning, it was a transition in a pre-existing, eternally inflating universe, one bubble among an effectively infinite number, each one a pocket universe with its own Big Bang, its own history, its own physical evolution. Now I want to push into what this actually means, not just as a cosmological story, but as a physical framework with specific consequences for the deepest questions in physics. Questions about why the laws of nature are what they are, about why the constants of physics, the strength of gravity, the mass of the electron, the value of the cosmological constant, have the specific values they do, about whether these values are determined by some deep physical principle or whether they're as contingent as the city you were born in. Because eternal inflation, combined with string theory's landscape of possible physical laws, suggests something genuinely radical, that the laws of physics are not unique, that they could have been different, that in other bubble universes they are different, and that the specific values we observe, the specific laws we live under, may be explicable not by some deeper physical necessity, but by the simple fact that we could only have evolved in a universe where these particular values permit life. This is the anthropic principle, and it's one of the most contested ideas in modern physics. Let me take you through it carefully, because the argument is more sophisticated and more physically grounded than its critics often acknowledge. Start with the cosmological constant. This is the single most dramatic example of the anthropic argument, and it's the one that has done the most to rehabilitate the principle in the eyes of serious physicists. We discussed the cosmological constant problem in our conversation about the Hubble tension, The quantum vacuum empty space has energy arising from quantum fluctuations of all the fields that permeate space. The theoretical calculation of this vacuum energy gives a value about 10^120 times larger than the observed value of the cosmological constant. This is the worst prediction in the history of physics. It's the largest discrepancy between theory and observation in science. One obvious response is that there's some unknown mechanism that cancels the vacuum energy almost perfectly, that whatever physics lies beyond the standard model arranges for the contributions from all the fields to cancel to. Extraordinary precision. But this cancellation would have to be accurate to 120 decimal places, a fine-tuning so extreme that it seems to demand explanation as much as the original discrepancy. In 1987, before the accelerating expansion of the universe was observed, before dark energy was discovered, Steven Weinberg made a remarkable prediction using the anthropic principle. He asked, if the cosmological constant can take a range of values in different regions of the universe, what values would allow galaxies, stars, and planets, and therefore observers, to form? The answer is constrained. If the cosmological constant is too large and positive, if dark energy is too strong, it drives the universe to expand so rapidly that matter can never clump together. Galaxies never form. Stars never form. There are no planets. There are no observers. If the cosmological constant is too large and negative dark energy pulling things together rather than pushing them apart, the universe collapses back on itself long before stars can form and evolve. Again, no observers. The range of cosmological constant values compatible with the existence of observers is narrow. Weinberg calculated it and found that the predicted range was roughly consistent with the value that was actually observed in 1998 when astronomers discovered the accelerating expansion. The cosmological constant is approximately 10^-123 inches, Planck units extraordinarily small, but not zero. And it's within the anthropic window, the range that allows observers to exist. This was not a post hoc explanation. Weinberg made the prediction before the value was measured. The anthropic argument gave a correct prediction of a fundamental physical constant, arguably the only successful prediction of this kind in the history of physics. Now let me explain why this is significant beyond the specific case of the cosmological constant. The traditional approach to explaining physical constants is to find a deeper theory, a theory that predicts the constants from first principles. The dream of theoretical physics, since at least Einstein, has been a theory so constrained that it uniquely predicts all the constants of nature, a theory of everything that leaves no free parameters, in which the electron has the mass it has, and the fine structure constant has the value it has, and gravity is as strong as it is, because there's simply no other consistent way the laws of physics can be, because the universe could not have been any different. This dream, the uniqueness dream, has motivated the search for string theory, for grand unified theories, for supersymmetry. The hope is that the underlying mathematics is so tightly constrained that only one set of physical constants is consistent with a self-consistent theory. But string theory has not delivered this. Quite the opposite. String theory appears to predict not one unique set of physical constants, but an enormous number, the landscape of string theory, with approximately 10,500 different possible vacuum states, each corresponding to different compactifications of the extra dimensions and therefore different effective physical constants. Different values of particle masses, different strengths of forces, different values of the cosmological constant. 10,500 possible universes, each with different physics, no unique prediction. For many physicists, this was a catastrophe. String theory was supposed to uniquely determine the laws of physics to tell us why nature chose these constants and not others. Instead, it gave a vast landscape of possibilities and no clear mechanism for selecting among them. But here's the radical reframing that eternal inflation offers. In an eternally inflating universe, the landscape is not a problem, it's a feature. Each bubble universe in the eternally inflating sea corresponds to one of the 10,500 possible vacua in the string theory landscape. Different bubbles have different physical constants. The landscape of possibilities is physically realized. All 10, 500 options actually exist in different pocket universes. And in that context, the anthropic principle becomes not just a philosophical argument, but a physical mechanism for explaining why we observe the constants we do. Of the 10, 500 possible sets of physical constants, some allow galaxies and stars and chemistry and life. Most don't. The vast majority of bubble universes are sterile. Their constants either make atoms impossible, or stars too short-lived, or nuclear chemistry too impoverished to support complex molecules. We observe the constants we do because we're in one of the rare bubbles where the constants are compatible with our existence. This is not mysticism. It's selection bias. If you survey 1 million planets for life and find it on a few, you shouldn't be surprised that the ones with life have conditions compatible with life. The selection effect, the fact that only certain conditions allow observers, explains the correlation between the constants in life without requiring any fine-tuning of a single universe. Now I want to engage with the serious objections to this picture because they're genuinely important and I don't want to paper over them. The first objection is the most fundamental. The multiverse is unobservable. The other bubble universes are beyond our horizon, forever inaccessible. If a theory predicts unobservable things, how is it different from metaphysics? How can we call it science? I've addressed a version of this in part 1, the observation that indirect evidence can confirm theoretical structures even when the structures themselves are unobservable. But there's a sharper version of the objection specific to the multiverse. If there are infinitely many bubble universes with all possible properties, doesn't that make the theory unfalsifiable? Can any observation be inconsistent with the multiverse? If anything we observe can be explained by saying we're in the right bubble, isn't the theory vacuous? This is the measure problem, and it's genuinely serious. In an infinite multiverse, where everything that can happen does happen somewhere, how do you make meaningful predictions? How do you calculate the probability of any given observation? Probability requires a reference class, a set of possibilities with weights. In an infinite multiverse, defining that reference class, defining what counts as a typical observer, how to weight different bubble types is deeply ambiguous. The measure problem is not solved. It's one of the most actively discussed technical problems in theoretical cosmology. Without a solution, the multiverse cannot make sharp quantitative predictions. Different measures, different ways of defining what's typical in the multiverse give different predictions for what observers should expect to see. Some measures reproduce Weinberg's cosmological constant prediction. Others give different answers. Until the measure problem is solved, the predictive power of the multiverse remains limited. This is a genuine limitation. And I want to be honest about it. The multiverse picture is motivated by solid physics inflation, the BGV theorem, the string theory landscape. But it's not yet a fully predictive scientific theory. It's a framework with enormous promise and serious unresolved technical problems. The second serious objection is what philosopher Tim Maudlin has called physics envy, the concern that the anthropic multiverse doesn't actually explain anything. When we ask why the cosmological constant is 10, negative 123, and the answer is because we're in one of the rare bubbles where it's compatible with life. That's a selection effect argument. But selection effects don't make predictions. They explain why we observe something but don't predict what we'll observe next. A genuine physical theory makes predictions. The anthropic principle, in its pure form, makes none. This objection has force. But it's somewhat overstated. The anthropic principle, combined with specific multiverse models, does make some predictions not about the exact value of constants, but about their rough order of magnitude and their relationship to observational requirements. Weinberg's cosmological constant prediction is the strongest example, a genuine prediction made before the observation, with an anthropic argument doing real work. Whether this constitutes enough predictive power to count as real science is a philosophical question on which reasonable people disagree. My own view is that the anthropic principle is a legitimate tool when used carefully and in conjunction with specific physical models, but that it becomes dangerously easy to abuse, explaining anything post hoc by saying we're in the right bubble. The discipline of genuine anthropic reasoning is to make the reasoning precise, to calculate the anthropic window, to predict the distribution of observables, to make testable claims, rather than to gesture vaguely at selection effects. Now let me tell you about something that I think is even deeper than the anthropic principle debates. Something about what the multiverse implies for the very concept of physical law. We've always assumed implicitly, profoundly, that the laws of physics are universal, that they apply everywhere at all times in the same way. That when we write down the equations of quantum mechanics or general relativity, we're writing down facts about the universe that are as true in the Andromeda galaxy as they are here, as true at the Big Bang as they are today. This universality of physical law is not something we've proven. It's an assumption, the most fundamental assumption of physics. And it's been extraordinarily successful. Every experiment we've conducted, every celestial object we've observed, every cosmological measurement we've made, all are consistent with the same laws holding everywhere we can look. But in the multiverse, physical law is not universal. It varies from bubble to bubble. The laws that govern our bubble, the standard model, general relativity, the specific values of all the constants, are local laws. They're the laws of our pocket universe. Other bubbles have different laws, different particles, different forces, different kinds of possible chemistry, different structures of matter, different, in the most extreme cases, different numbers of spatial dimensions, different relationships between quantum mechanics and gravity. What remains universal in the multiverse picture is something more abstract. The meta-laws, the laws that govern how the landscape of possible laws is populated, how bubbles form, what range of physical constants is possible in principle. String theory, if correct, provides these meta-laws. The 10,500 possible vacua represent the range of possible physics constrained by the meta-laws of string theory. Within that range, specific local laws are selected by what? By the tunneling dynamics that determine which bubble forms from which, by the anthropic selection that determines which bubbles contain observers, by chance. This is a genuinely revolutionary picture of what physics is. Not the discovery of unique, universal laws that were always there waiting to be found, but the exploration of a landscape of possibilities in which our particular laws are one point distinguished not by uniqueness but by habitability. Let me now bring in something that I think adds a dimension to this story that's often missing. The role of quantum mechanics in the very beginning. Inflation, as I described it, is a classical story. The inflaton field rolls down its potential energy curve, driving exponential expansion, eventually ending in a hot Big Bang. Quantum fluctuations are present. They're responsible for the density fluctuations that seed large-scale structure, and they're responsible for the randomness that makes inflation eternal. But the overall story is told in classical language. At the absolute boundary of eternal inflation, at the point where the BGV theorem says there must have been a beginning, classical language breaks down. The universe is small enough that quantum gravitational effects dominate. Space-time itself is quantized. The distinction between space and time may dissolve. The concept of a smooth classical geometry, the geometry that general relativity describes, may not apply. In this quantum gravitational regime, the beginning is not a sharp event, it's a quantum blur. The Hartle-Hawking wave function of the universe describes a probability distribution over different initial states, not a single definite initial condition. The universe didn't start from one specific state and evolve deterministically from there. It started from a quantum superposition of states, and the classical universe we observe is one branch of that superposition. This connects to something profound about the relationship between quantum mechanics and the cosmos. In ordinary quantum mechanics, applied to particles and fields, measurement collapses the wave function and selects a definite outcome. But in quantum cosmology, in the wave function of the entire universe, there is no external observer to perform the measurement. The universe must somehow select its own state. How it does this, how the quantum superposition of possible universes resolves into the specific classical universe we observe, is the quantum cosmological version of the measurement problem. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, where collapse is caused by measurement, quantum cosmology faces a fundamental problem. Who measures the universe? In the many worlds interpretation, where all branches of the wave function are equally real, quantum cosmology is actually more natural. All branches exist, all possible universes are realized, and we're in one branch by virtue of existing. The many worlds interpretation and the multiverse of eternal inflation naturally reinforce each other. Both picture a vast multiplicity of actually existing realities, with our universe being one branch or bubble. In the decoherence-based approaches, where the classical world emerges from quantum mechanics through the interaction of quantum systems with their environments, quantum cosmology requires understanding how the early universe decohered from a quantum superposition into the specific classical initial conditions of our Big Bang. This is an active research area, and the answers are not yet clear. But the point I want to make is this. Quantum mechanics applied to the universe as a whole suggests that the beginning was not a sharp classical event. It was a quantum transition from a state in which classical time didn't exist to a state in which classical time emerged. And the specific classical state that emerged, the specific initial conditions of our Big Bang, may have been selected by the quantum dynamics of the wave function of the universe. The beginning was quantum. And quantum beginnings are not the sharp, clean starts that classical physics imagines. They're fuzzy, probabilistic, multiply, realized. They're consistent with the multiverse picture at a fundamental level. Let me now tell you about a specific, technically precise result that I think illuminates the pre-Big Bang question in a way that's often overlooked. It comes from thermodynamics, specifically from the concept of entropy. The second law of thermodynamics, the law that entropy always increases, is one of the most fundamental and best established laws in physics. Every physical process moves from lower to higher entropy. Disorder always increases. The past is lower entropy than the future. This asymmetry, the thermodynamic arrow of time, is why we remember the past but not the future, why broken eggs don't spontaneously reassemble, why stars burn but don't unburn. Now, here's the thermodynamic puzzle about the Big Bang. Our universe started in an extraordinarily low entropy state. The Big Bang initial conditions were remarkably ordered, smooth, uniform, with tiny density fluctuations that gravity could then amplify into stars and galaxies. This low initial entropy is what allows the second law to operate. Entropy has been increasing since the Big Bang because it started low, but why did the Big Bang start in a low entropy state? By ordinary probability, you'd expect the initial conditions to be high entropy, disordered, uniform, in a featureless way, without the specific ordered fluctuations that allowed structure to form. Low entropy initial conditions are extraordinarily special. They're the configurations that require explanation. The physicist Roger Penrose has estimated that the probability of the Big Bang happening to start in the low entropy state it did, given a random choice from all possible initial states, is approximately 1 in 10, 10, 123. That's not a typo. It's 10 to the power of 10 to the power of 123. A number so vast that writing it out would require more digits than there are atoms in the observable universe. It's not just unlikely. It's so far beyond unlikely that the word doesn't apply. Penrose's own solution to this is conformal cyclic cosmology, the idea that the universe goes through cycles, with the end of each cycle a heat death being conformally equivalent to the beginning of the next cycle, a Big Bang. This is an interesting proposal, but not widely accepted. The eternal inflation response is different. In eternal inflation, the low entropy of the Big Bang is not a coincidence. It's a selection effect. The eternally inflating background is itself in a very specific quantum state, a state that generates bubbles with specific properties. The bubbles that form in ways compatible with the existence of observers necessarily have the low entropy initial conditions that allow the thermodynamic arrow of time to operate. Because without that arrow, no complex structures, no chemistry, no biology, no observers would form. We're in a low entropy bubble because high entropy bubbles don't produce observers to notice them. This is the anthropic principle applied to thermodynamics. And it works. In the same way it works for the cosmological constant, it explains why we observe something that looks extraordinarily special by noting that the unspecial alternatives don't produce observers. Now let me bring this discussion to something that I find genuinely beautiful. A connection between the pre-Big Bang physics, the multiverse, and the observational program of 21st century cosmology. If we live in one bubble in an eternally inflating sea, and if our bubble occasionally collides with neighboring bubbles, those collisions leave observable imprints. I mentioned this briefly in part 1. Let me be more specific. When two bubble universes collide, the collision creates a disturbance, a wave that propagates through our bubble. This wave leaves a specific calculable imprint on the CMB, a circular disk of altered temperature and polarization with specific properties that depend on the energy of the collision and the properties of the neighboring bubble. Different collision scenarios make different predictions for the size, contrast, and polarization pattern of the imprint. The Planck satellite and its predecessors have searched for such imprints, circular anomalies in the CMB that might signal a bubble collision. So far, no confirmed detection. But the searches have not yet exhausted the theoretically predicted parameter space. Future CMB surveys, including the Simons Observatory and CMB S4, with dramatically improved sensitivity and resolution, will push the search further. A confirmed detection of a bubble collision imprint would be transformative. It would provide direct observational evidence that other bubble universes exist, that eternal inflation is real, that the Big Bang was not the beginning but a transition, that we are one bubble in a much larger structure. It would be the most significant observational discovery in the history of cosmology, arguably the most significant in the history of science. And a null result, a failure to detect any such imprint after exhaustive search, would constrain but not rule out the multiverse picture. It would mean that either no collision has occurred within our observable volume, or the collision occurred but the imprint is too faint to detect, or the specific parameters of eternal inflation are such that collisions are extremely rare in our region. The search continues. The data are coming. And the stakes, whether the Big Bang was the beginning or a transition, could not be higher. Let me now take you to something that reframes everything we've discussed in a way that I find genuinely profound. We've been asking, what was there before the Big Bang? And the answer eternal inflation gives is more space, more time, more physics, more of the same fundamental process. An inflating background, a quantum beginning before that, a landscape of possibilities instantiated in infinitely many bubbles. But there's a deeper version of the question that I want to raise. Not what was there before the Big Bang in a temporal sense, not what physical process preceded it, but why was there anything at all? This question has been asked by philosophers since Leibniz posed it 3 centuries ago. Why is there something rather than nothing? And physics, for most of its history, has treated this as outside its domain. Physics describes what is. It doesn't explain why there is something rather than nothing. That's metaphysics. Or theology. Or meaningless word games. But quantum cosmology, Hartle, Hawking, and Vilenkin attempts to answer it. And the answer is, nothing is unstable. The quantum mechanical laws that govern everything, including the universe itself, imply that the probability of nothing spontaneously transitioning to something is non-zero. Not certain, not inevitable, but non-zero. Given infinite time, even an improbable quantum event occurs. And from a quantum vacuum, from the state of minimum energy, minimum information, minimum everything, a universe can emerge. This is not a complete answer. It raises its own question. Where do the quantum mechanical laws come from? Why is the quantum vacuum the kind of thing that can generate universes? Why is there a quantum vacuum rather than literally nothing at all, not even the laws of quantum mechanics? These questions press toward the edge of what physics can address, possibly beyond that edge. The famous physicist Richard Feynman, when asked about the deepest questions, used to say that nature is what it is, and our job is to figure out what it is, not to ask why it has to be that way. The laws of physics are what they are. We describe them. We don't derive them from something deeper, but the multiverse picture suggests that even this attitude may need revision. If the laws of physics vary from bubble to bubble, if our local laws are just one point in a landscape of possibilities, then the question of why the laws are what they are is a legitimate physical question with a physical answer. Because among all possible laws, these are the ones in the subset compatible with observers. Why does something exist rather than nothing? Because something includes the laws of quantum mechanics, which are unstable to generating universes. And why do the laws of quantum mechanics exist? We don't know. That's where physics currently stops. But physics has moved the boundary. The question, why does our universe have these properties, now has a partial answer, a genuine physical anthropic answer. And the question, why does something exist, has been pushed back to why do the laws of quantum mechanics exist? A harder question, but a more precise one. Progress in physics often consists not of answering questions, but of asking better ones. The multiverse, for all its uncertainties, is asking better questions about the nature of reality than any previous framework. I want to close this second part with something that I think captures this strange, beautiful, vertiginous quality of where we've arrived. We started with the Big Bang, the event that cosmology has long described as the beginning of everything. Space, time, matter, energy, all beginning 13.8 billion years ago in a state of infinite density and temperature, a singularity, the beginning. We followed the physics inflation, eternal inflation, the BGV theorem, the string theory landscape, quantum cosmology, and we've arrived somewhere completely different. The Big Bang was a transition. Before it, an eternally inflating sea. Before that, a quantum origin, fuzzy, probabilistic, perhaps timeless. Around it, infinitely many other bubble universes, each with their own physics, their own laws, their own history, and the physical constants. We observe the mass of the electron, the strength of gravity, the value of the cosmological constant. These are not fixed by some deep necessity. They're the values in our particular bubble. They could have been different in other bubbles. They are different. We observe these values because they're in the anthropic window, because a different set wouldn't have produced observers to measure them. This is a universe so much larger, so much stranger, so much more extraordinary than the one we thought we had, that the word universe, from the Latin universus, meaning turned into one, referring to the totality of everything, no longer seems adequate. We need a new word. Cosmologists have proposed one, the multiverse. Many universes, many totalities, an infinite sea of Big Bangs, each one someone else's beginning. In part 3, I want to bring this all the way home. To ask what this means, not just for physics, but for us, for our understanding of our place in the cosmos, for the relationship between physics and meaning, for the question of whether the extraordinary specificity of our universe, its fine-tuned constants, its improbably low entropy beginning, its long and patient production of life and mind, is pointing at something, or is itself explained by the cold logic of selection effects in an infinite landscape. We were wrong about the Big Bang being the beginning. What else might we be wrong about? So we'd arrived at this place where the Big Bang is not the beginning, but a transition, one bubble forming in an eternally inflating sea, surrounded by infinitely many other bubbles, each with different physical laws, all of them together constituting a multiverse so vast that the word universe no longer means what it used to. And I've laid out the physics carefully. Inflation, eternal inflation, the BGV theorem, the string theory landscape, the anthropic principle, each piece connected to the next. Each following from physics, we already have good reason to believe. Now I want to do something different. I want to ask what this means, not just scientifically, but existentially, for our understanding of who we are, where we came from, and what it means to be the kind of creature that can ask these questions at all. Because I think the multiverse picture, if it's right, and it might be, in some form changes something fundamental about the relationship between physics and human meaning. Not by making the universe meaningless, as some people fear, but by changing what kind of meaning is available to us, what kind of answers physics can give, and what kind of questions remain permanently beyond its reach. Let me start with what I think is the most important and most underappreciated consequence of the multiverse picture. Not the vastness of the multiverse, not the multiplicity of physical laws, but something more intimate. It's this. In the multiverse picture, physics cannot, even in principle, give us a uniquely determined answer to the question, why are the laws of physics the way they are? The dream of Einstein, a theory so constrained that it uniquely determines all the constants of nature, leaving no room for them to be otherwise, is, in the multiverse picture, not just unfulfilled, but unfulfillable. The constants could have been different. In other bubbles, they are different. The specific values we observe are not necessary. They're contingent. This is a profound shift in what physics is for. For most of the history of modern science, the goal has been to explain why nature had to be this way. Why the speed of light is what it is, why the electron has the mass it has, why gravity is as weak as it is. The hope was that a deep enough theory would show that the constants are uniquely determined, that the universe couldn't have been otherwise. The multiverse says, it could have been otherwise, and it is otherwise, somewhere. The constants we observe are not the unique correct values. There are values, the values in our bubble. They're contingent on the specific vacuum our bubble happened to nucleate in, and they're constrained within that contingency by the requirement that they be compatible with our existence. This doesn't mean physics has failed. It means physics has discovered something that the laws of nature are not necessary but contingent, not unique but one among a vast landscape of possibilities. This is a discovery, not a defeat. Just as the discovery that Earth is not the center of the universe was a discovery, not a defeat, even though it displaced us from cosmic centrality. But it does mean that the explanation physics can give for why the constants have their specific values is different from what we hoped for. Not because the mathematics uniquely requires it, but because this is one of the relatively rare sets of values compatible with complex chemistry and observers. And we're observers. Now let me address something that I think is genuinely philosophically important. The concern that the anthropic explanation is not a real explanation, that's saying we observe these constants because we're here to observe them, is circular or empty or trivially true. The concern has force. Selection effects can masquerade as explanations. If you find a group of people who all survived plane crashes and note that they're all lucky, well, only lucky people survive plane crashes. That's not an explanation of their luck. It's a tautology. But the anthropic explanation of the cosmological constant, Weinberg's prediction, is not a tautology. It's a genuine prediction. Let me be precise about why. Weinberg didn't just say the cosmological constant must be compatible with our existence. He calculated the range of values compatible with galaxy formation, the anthropic window. And then he predicted that the cosmological constant, if it varies across the multiverse, should be found somewhere in this range, probably near the upper end where the fraction of observers is maximized. And when the cosmological constant was measured in 1998, it was in this range. This is a real prediction. It would have been wrong if the cosmological constant were 0, or much larger, or negative with large magnitude. The anthropic argument makes a specific quantitative prediction that could have failed and didn't. the strength of the anthropic argument is not in explaining why the constants are exactly what they are. It doesn't do that, and it can't. The strength is in explaining why they're in the general range they are, why they're compatible with the existence of observers. The argument narrows down the expected range of values from 10, 120 possible values to a small window and predicts that we'll find the constants in that window. And we do. That's not nothing. That's real scientific work. But here's where I want to push further, into something that I think is even deeper than the anthropic argument, something about the relationship between consciousness and the multiverse. We've established that the anthropic principle operates by selection. Only certain bubble universes produce observers. The constants in those bubbles are the ones compatible with observers' existence. We observe the constants we do because we're observers. But what is an observer? In physics, the word observer has a technical meaning. An observer is any physical system that interacts with a quantum system and records the outcome. A particle detector is an observer. A photographic plate is an observer. Technically, no consciousness is required. But in the context of the anthropic principle, observer typically means something more. It means conscious observers, beings capable of asking why the constants have the values they do. Because it's only conscious observers who can perform the anthropic reasoning, who can notice the fine-tuning, who can wonder about it. And here's where the multiverse and consciousness connect in a way that I find extraordinary. Consciousness, or at least the kind of complex information processing that produces conscious experience, requires specific physical conditions. It requires chemistry, specifically carbon-based chemistry of extraordinary complexity. Carbon forms long-chain molecules, organic molecules, with the specific bonding properties that allow the construction of self-replicating systems, metabolic networks, and ultimately neural networks. The reason carbon is special, the reason life is carbon-based rather than silicon-based or iron-based, is that carbon's electronic structure, determined by the fine structure constant and the masses of the fundamental particles, gives it uniquely versatile bonding properties. If the fine structure constant were different by a few percent, carbon wouldn't have these properties. If the strong nuclear force were weaker by a few percent, carbon wouldn't exist. The nuclear reactions that produce carbon in stellar cores wouldn't proceed. The specific constants that allow carbon chemistry and therefore life and therefore consciousness and therefore the anthropic reasoning about the constants are a tightly constrained set. We're in a universe where physics allows consciousness because physics allows carbon, because physics allows the right kind of nuclear reactions, because the constants happen to be in the right range, and we're asking why. And the answer in the multiverse picture is a circle that completes itself. Consciousness exists in this universe because this universe's constants allow consciousness to exist. And this universe is the one we observe because we're conscious. This circularity is not a problem. It's a description. The anthropic principle is a description of the selection bias built into any observation made by any conscious being anywhere. It's saying you will always find yourself in a universe compatible with your existence, because if you weren't in such a universe, you wouldn't be there to notice. But it leaves open a deeper question. Is consciousness something the universe was going to produce anyway, an inevitable consequence of a universe with the right constants, or is consciousness extraordinarily rare, something that happened on this planet, perhaps nowhere else in our entire observable universe? The multiverse doesn't answer this, but it changes how we should think about it. Let me tell you about something that I find genuinely moving about the multiverse picture, even though I recognize that moving is not a scientific criterion. In the pre-multiverse picture of cosmology, our universe was the universe, all of physical reality, everything that exists. And in that picture, the extraordinary specificity of our universe, its fine-tuned constants, its low entropy beginning, its long, patient production of stars and planets and chemistry and life, seem to cry out for explanation. Why these constants? Why this beginning? Why us? Some people found religious significance in this fine-tuning. The constants are precisely what they need to be for life to exist. Doesn't that suggest someone designed it that way? The multiverse provides a scientific alternative to this reasoning. Not because it disproves design, the multiverse doesn't touch theological questions about whether a creator exists, but because it changes the explanatory landscape. In a multiverse with all possible constants, the fine-tuning of our universe isn't surprising, it's expected. Any observer asking why their universe's constants are compatible with life will always find the answer is yes, because they couldn't be asking if the constants weren't compatible with their existence. The feeling of significance, the sense that our universe was specially arranged for us is real. But in the multiverse picture, it's a selection effect. Every observer in every bubble experiences the same feeling. Every observer finds themselves in a universe compatible with their existence. The feeling of specialness is universal. And therefore, paradoxically, no universe is more special than another. I find this simultaneously deflating and exhilarating. Deflating because the sense that our universe was made for us, or at least made just right for life, turns out to be a tautology. Exhilarating because it means the universe is even more vast, more various, more extraordinary than we imagined. There are infinitely many bubbles, each with its own physics, its own chemistry, its own possible forms of complexity and observer. The cosmos is not a single, carefully arranged stage. It's an infinite proliferation of stages, each with different plays, most of them empty of any audience. And we happen to be one of the audiences in one of the stages, under one set of physical laws, wondering how it all works. Now I want to connect all of this to a question that I think deserves a direct answer. A question about the future of physics. If the multiverse picture is right, if the constants of nature are contingent, selected anthropically from a landscape of possibilities, what does this mean for the future of fundamental physics? What are we trying to do? What counts as progress? The traditional goal of fundamental physics is unification and explanation. Find the deepest laws, derive everything from them, explain why the constants have their values. This is the dream of a theory of everything, a single mathematical framework from which all of physics follows. In the multiverse picture, this dream is partially undermined. A theory of everything, if string theory is correct, gives us the meta-laws, the landscape of possibilities. But it doesn't uniquely determine the specific laws in our bubble. The best physics can do is calculate the probability distribution over possible universes and identify the anthropic window. It can tell us what range of constants is compatible with observers. It can't tell us why we're at this specific point in the range rather than another. Does this mean physics stops making progress? No. There are still deep questions that the multiverse picture doesn't answer. Questions that require a complete theory of quantum gravity, a better understanding of the string theory landscape, a solution to the measure problem, an understanding of how our specific bubble formed and why it has the specific low entropy initial conditions it does. And there are questions that the multiverse opens up rather than closing down. What is the distribution of properties across bubble universes? What fraction of bubbles are hospitable to any form of life? How common is chemistry of the type that produces observers? Are there forms of complexity forms of what we might broadly call life or mind that exist in bubbles with very different physics from ours? These are scientific questions. They have answers even if the answers are not directly observable. And the project of theoretical physics, combined with the observational program of CMB cosmology and gravitational wave astronomy and exoplanet characterization, is beginning to address them. Physics is not ending in the multiverse picture. It's transforming. The questions are harder. The answers are more statistical. The connection between theory and specific observation is more tenuous. But the enterprise of understanding what the universe is and why continues. Let me now come to something that I've been building toward throughout this entire conversation. The deepest implication of the pre-Big Bang picture. We've established that the Big Bang was not the beginning. Before it, eternal inflation. Before that, a quantum origin. Surrounding it, infinitely many other bubbles. And before all of that, the laws of quantum mechanics themselves, which seem to be necessary for anything to happen at all, but whose own origin is beyond current physics. In this picture, what is the relationship between the universe and the observer, between physics and consciousness, between the laws of nature and the minds that discovered them? I've been thinking about this for a long time, and I want to give you an honest answer rather than a tidy one. The multiverse picture seems to make the universe vast and impersonal. Infinitely many bubbles, most of them sterile, the few with observers being no more significant than the sterile ones except from the perspective of the observers themselves. Consciousness is a selection effect, not a cosmic necessity. Mind emerges from physics by accident, by the anthropic luck of being in a bubble with the right constants, not because the universe was building toward mind. This is a deflating picture for those who find meaning in cosmic significance. The universe, in this picture, is not arranged for us. It's not moving toward anything. It's not an arrow pointed at consciousness. It's a quantum foam generating bubbles forever, most of them empty of any awareness, and we're in one of the minority that isn't. And yet, something in this picture, when I sit with it carefully, seems to me to point in a different direction. Not toward the conclusion that we don't matter, but toward the conclusion that we matter in a very specific, very real, very unusual way. In this vast, mostly sterile multiverse, in this infinite proliferation of bubbles, most of them playing out their physics in complete darkness, with no one to observe, no one to notice, no one to understand in some of them, something extraordinary happened. The constants fell in the right range, chemistry became possible, life emerged, minds arose, and those minds looked up at the sky and began to understand, not just to exist, to understand, to trace the laws of physics back to the Big Bang, through inflation, past the BGV boundary, to a quantum origin that preceded everything, to discover that we're in a bubble, to understand the landscape, to figure out the anthropic argument, to know with genuine precision something about where we came from and what the larger structure looks like. This capacity, not just to exist but to understand, is rare, maybe extraordinarily rare, and it's us, right here, right now. The universe, in the vast majority of its instantiations, produces no understanding. It runs its physics in silence, in darkness, without witness. And in the tiny fraction where understanding arises, where minds capable of cosmological reasoning appear, something happens that doesn't happen anywhere else. The universe becomes, in those places, aware of itself, capable of asking why. Capable of being wrong about whether the Big Bang was the beginning, and then discovering its wrongness and revising its understanding. That's not nothing. That's not a selection effect to be explained away. That's the most remarkable thing I know of in the entire physical universe. Let me bring this all the way back to where we started. We were wrong. I said that at the beginning. And I've traced through what we were wrong about and why we were wrong and what the corrected picture looks like. The Big Bang wasn't the beginning. It was a transition. Before it, an eternally inflating sea. Before that, a quantum origin. Around it, infinitely many other universes. But I want to say something about the wrongness itself, about what it means to be wrong in the way we were wrong. We were wrong because we extrapolated a successful theory, the Big Bang model, to a regime where it doesn't apply the singularity the moment before the expansion. We assumed that because the Big Bang model worked magnificently for the past 13.8 billion years, it must be the complete story extending back to a definite beginning. We conflated the validity of the model in its domain of applicability with the scope of what the model describes. This is a very human mistake. And it's a mistake that physics makes repeatedly, not because physicists are careless, but because the boundaries of a theory's validity are not always apparent until you push against them. Newton's mechanics worked brilliantly until relativistic speeds. The Big Bang model worked brilliantly until the singularity. String theory is working brilliantly at explaining the landscape until we don't know yet. The pattern of this mistake and the pattern of its correction is the deepest rhythm of physics. A theory succeeds. It explains everything in its domain. It seems complete. Then a new observation or a new theoretical insight reveals that the domain was smaller than we thought. There's more beyond the boundary. And the new theory, while it must reduce to the old one within the old domain, extends beyond it in ways that are genuinely surprising, genuinely strange, and genuinely more accurate. The Big Bang model is not wrong. It's correct in its domain. From 1 second after the beginning of our bubble to today, the correction is not to the model. It's to the interpretation, to the claim that the model's domain is all of physics, that the beginning of our bubble is the beginning of everything. We were wrong about the scope, not the content. And understanding the scope, understanding what lies outside the domain, what preceded the Big Bang, what surrounds our bubble, is where physics is now working. Here's what I want to leave you with. Something about what it means to do physics in an era when the questions are this deep and the answers are this uncertain. Physics has always been the project of understanding what the universe is. At its best, it proceeds by following the mathematics wherever it leads, even when it leads somewhere unexpected, counterintuitive, or disturbing. The history of physics is full of moments when mathematics led to something that seemed impossible. Curved space-time, quantum superposition, the expanding universe, and turned out to be correct. The mathematics of eternal inflation leads to a multiverse. The mathematics of the string theory landscape leads to 10,500 possible sets of physical laws. The mathematics of quantum cosmology leads to a universe that tunneled from a timeless quantum state. These conclusions are disturbing, they're unobservable in detail, they're statistically rather than uniquely predictive, they undermine the dream of a theory that uniquely determines everything, but physics has no choice but to follow the mathematics. That's the discipline, that's the commitment, that's what distinguishes physics from wishful thinking, the willingness to accept what the equations say, even when the equations say something you didn't want to hear. The equations are saying the Big Bang wasn't the beginning. The universe is vastly larger, vastly older, vastly more various than we thought. Our physical laws are contingent. Our existence is an anthropic selection effect in a mostly sterile cosmos. And also, in that mostly sterile cosmos, we are the places where the mathematics became aware of itself, where the equations turned around and looked back at the reality they describe, where the physics-generated minds capable of asking whether the Big Bang was really the beginning. It wasn't. But the question was worth asking. And the answer, strange and vertiginous and unfinished as it is one of the most extraordinary things the universe has ever produced. A bubble of space-time, 13.8 billion years old, containing minds capable of discovering that they're in a bubble. That's us. That's here. That's now. We were wrong about the beginning. And being wrong carefully, rigorously, following the physics until the wrongness became undeniable is exactly how we found out what's actually